Hello, everyone. My name is Keen. I'm a senior data scientist at Gousto, and so today I'll be showing you how we've been using simulation to improve the efficiency of our production. Um, there you go. So I'll share a bit of context around the company, who we are, what we do, why we decided to use simulation, how we've decided to use simulation, and at the end of the presentation, I'll show you the actual use case and the result we've actually had with this implementation. So first, a bit of context. What's Gousto, who we are? We like to call ourselves a scale-up tech company that delivers food. So what does that mean? Um, so we deliver recipe boxes, which means that every week, if everyone wants to eat nice food. A lot of people want to cook their own meal, but don't necessarily have the time to think about the recipes they want to cook, to go to the supermarket, to organize themselves. And so that's where Gousto comes in. You connect on the app, you choose the recipes you want to cook for your week. You validate your order, and then you delivered a box with all of the ingredients that you need in exact quantities for the recipes you need to cook, so you have zero waste. And it comes along recipe cards with instructions to follow on how to cook your recipes. So it could be, anywhere from 10-minute fast recipes to healthy recipes to heavy meat lovers, all these kind of things. Gousto has been around since 2012. So that's why we're not a startup anymore, but we keep the startup mindset. And in 2023, Gousto generated 308 million pounds in revenue. So we start being fairly big. So what sets us apart from the competition? Well, the main differentiator is choice. You have access to more than 250 different recipes every month. So it's a really big variety of recipes you can choose. And for anyone that, deals a bit with logistics and warehouses and things like that, that's really what creates a lot of challenges for us on the tech side. And we're able to do this while keeping the prices down. So you have access to offer from less than £3 per portion. And so we do that by focusing heavily on data and our tech, on artificial intelligence, and all of our tech products, which simulation wraps in nicely as part of that. And of course, we always obsess mainly over our customers. So how do you make a recipe box? I think the best way is to show you a bit of the simulation and explain you what happens in our factory. So as you can see at the bottom there, we have box erectors that will create the boxes, send them on different lines, different production lines. So this is one of our factory. And then you have one line per level of the in-feed of boxes. So the boxes come, they queue, they wait to be introduced into the pick tower. And then each box is going to be routed and with live routing of boxes. And for example, this box says, okay, you have to go to this station to pick up these ingredients. And so the box enters what we call a leg and then moves towards one of the stations. So as you can see here, box moving. And for example, you'll see at some point a box moving into a station. For example, just this one. And so at this point, what we're not showing on the video, sorry, is that in front and behind the pickers, you actually have a pick station. It's not empty like in the simulation. So you have a lot of what we call a pick station. You have pick faces with all of the ingredients in these blue dots. And so the box arrives, a bunch of lights light up to tell the picker which ingredients they need to pick. They pick the ingredients, put them in the box, press the button, the box is released, and then travels to the next station in line. And it repeats this operation until the box has picked all of the ingredients to exit the pick tower. So I said we have one line per level as in feed. But sometimes, due to operational problems, some stations are unavailable. And so sometimes a box needs to travel across levels to finish its picking. So basically what happens is that you have a kind of big interconnected maze of conveyor belts with boxes that can go anywhere across this 3D maze. And so once you've done all of that, then the boxes can finally be released and they exit the pick tower. And then what's not in the simulation there is that there's machines to automatically close the box, apply label, and send them to the palletizing area, where they then put on pallets and then sent to the customers. So that's how you make a box at Gousto. Now, why do we need simulation models for that? So what we had before, we had simulation as our development cycle was, well, you start at the top, you have a lot of ideas how to improve things. You you have to develop code for those ideas. Then you need to filter down and keep only the best ideas and actually often the safest ideas, which typically aren't the best ideas. And you have to choose the safe ideas because, well, a lot of problems can happen when you release into production. And so you make a lot of checks, you release to production, and then you check what happens. Sometimes it works, sometimes it doesn't. And so you go back on your feedback loop to the starting point. And because you're operating in the factory and you have only one factory, I mean, you have several, but when you deploy into a factory, you have only this one, and things can go wrong. So you need to be very, very careful. And so typically this cycle could take months. That's where simulation comes in, and you can change your development cycle because while you develop your ideas and your code, you can actually test quickly hundreds of ideas that you have in a safe environment inside the simulation, and you can iterate within the simulation. You'll keep your best ideas, you validate your code, and once you've done that and you're happy about the value that you're going to deliver, its improvements, at this point you can release to production. And because that feedback loop in a simulation takes days, you've actually gained an order of magnitude in your development cycle. And by the time you release to production, you're a lot more confident about not having any side effects. And then, of course, you always learn new things when you release to production. And so you, again, have this feedback loop, this major feedback loop to come back to the starting point. That's why we have simulation. And from the very beginning, we thought hard about how we're going to implement simulation. Sorry. Before that, I mean, it's sort of part of it, but yeah, how we're going to implement simulation and why do we choose AnyLogic for that? One of our main operating model is to have self-serve simulation, meaning we want to have as many people in the company using the simulation. And so for that, the AnyLogic standalone model export is very convenient because you only need a license per developer, not per user. So you can have a lot more users than developers. Also, we have a wide variety of operating systems. We operate on Mac, Linux, and Windows. So we needed a simulation model that was able to operate across platforms. And mostly, the way we want to develop, the way we have developed the simulation is to integrate our production code within the simulation. And because our algorithms are mainly Python-based, because we have data science algorithms, Python-based, we needed a way to integrate within a simulation environment our Python algorithms. And that's where the AnyLogic pipeline connector became very handy. And so these were choices we made before we chose AnyLogic as a software. Now I want to explain a bit more what is self-serve simulation and how it works. I'll show you a video in a minute, but I'll explain the flow before that. So, you're a coder in one of our squads working on something, and you make your code change on your actual package where you work usually. And the way we operate is you then update the simulation. Again, I'll show how it's done. You update the simulation so that the simulation integrates your version of your software. Then you run your AB experiment campaign, you run like dozens of different simulations with like how with your previous software and your new software, you might have to do a few feedback loops to make sure that you have what you want. And then once you're satisfied with it, you can prove the benefits, you go a bit higher up and you get approval for your software release, and then you release to production. So let me show you how that looks in reality. Well, imagine we have a data scientist or a software engineer working on this box routing Python package, which, as you remember what I said before, that's the software that controls where each box goes, to which station each box goes. So the first thing you do is you clone the simulation model repository. We've packaged the model exports and put it on GitHub to allow easy usage of it. So you clone the repository in that way. It takes maybe 30 seconds to do so. And then as soon as it's done, the next thing will be to update the simulation so that it knows that it needs to use your version of your software and not the default version. So you open the project configuration. As you can see here, we have box routing with a specific revision number, which is different than so that would be the default one, the one we use in production. And so actually we want to use this new version that the software engineer has developed. So he'll change the revision number here, and then he's going to recompile everything just by running the simulation actually. And I've coded things in the background so that it just does the recompilation automatically. So you just do, make GUI, and what's happening now is it's reinstalling all of the Python packages in the proper versions, including all the dependencies of this new repository. It only takes a few seconds, and then it runs the simulation, in this case, with the GUI. So as you can see here, this box routing package has been reinstalled. It's using the proper version now. And so when this simulation runs, each box that comes out now at the bottom here has been routed and has done the selection of which station to go to based on the software version that has changed, minutes ago. So it's a really, really quick feedback loop to do that, completely autonomous from the software engineer. And you change your inputs, of course. You can use some of the predefined test scenarios. And I always recommend anyone developing the software with the simulation to first use the GUI just to validate and try to make a small test case. Just validate that your change does what you think it does with the 3D interface, just a visual validation. But of course, that visual validation, it's a necessary step, but it's not enough to run the experiment, because with the experiment, you want to run maybe dozens, sometimes hundreds of simulations. And so you can't just be manually clicking to run simulations. And so for that, we've also exported the model to run without the GUI. And so if you do, another command like make no GUI, now it's running the same simulation a lot faster because it doesn't need any of the 3D interface. And so then on top of that, we have a lot of code wrappers that allow you to run simulation experiments, and it's going to loop across all of your inputs and run, for you 10, 20, 100 simulations. So yeah, that's how we've implemented a simulation for self-serve development. Now, sorry. There you go. Now the way it's built is you have the core simulation engine that's been developed with AnyLogic that incorporates the box flow in the peak tower. Inside the Java function, we have the replenishment of stock, we have consumption of stock each time. So we track the stock of each ingredient at each station. And when a box comes, it actually consumes from that stock. And then a few inputs. Of course, we have the mapping of ingredients to station, the initial stock, and then we have historical processing times, historical downtimes, and then the simulation needs to interface with the Python APIs. And so the same way as happens in reality, at a certain frequency, the simulation and reality, the program that handles the peak tower will request a certain number of orders to release to production. We're going to request these orders through this AnyLogic pipeline connector. And Python algorithm has access to the historical sequence of orders that we have to produce for that run, and the requirements, which order needs which ingredients, and some other information like everything that AnyLogic knows. And it's going to make a decision and route the orders, and that's the point where the simulation will release these orders and the box starts appearing. And we do the same for stock. We have a certain frequency request for new stock, because as we consume the stock, then we destroy the totes that are at the station, and then you have to have some new one coming. And so there's an algorithm for that uses a lot of information that we have on site, stock on site, pilot arrivals, forecast of consumption, forecast of arrivals, to decide which is the best stock to prioritize. Because sometimes you can have all stock everywhere, sometimes, and most of the times, because of the pressure of live production, you have to make some choices, right? So a special algorithm for this. And then this algorithm, same as in the factory, releases your new stock for the simulation. So I'll show you in a bit the use case that we've had, but before that, I want to show a few statistics. So we started using AnyLogic less than 2 years ago, is when we had the first license. Now we have 3 squads that use the simulation as part of their product development. They've solved more than 30 different use cases. And typically now there's a simulation, we've done more than 5,000 simulation runs since the beginning, simulated a bit more than 10 million boxes. And yeah, my favorite statistics is I've burned through 3 laptops already, because it's kind of intense on the laptop. So if you want to do large-scale simulation runs, you need to increase a bit your IT budget. So yeah, before I go into the actual use case, I just wanted to share some thoughts that I've had over the compromise between speed and code block programming. So speed and ease of use. The first version that I did of a simulation, the flow chart of it looked like this. And that was for only one of the 3 levels. So I made the forecast and I said, okay, what if we had this for the entire factory, for entire peak tower? I would need 700 code blocks. And based on how it scales with the numbers, I estimated it would take me around 48 hours to run 40,000 orders, which is typically the size of our simulations nowadays. So not really useful for fast iteration. So I went back to the drawing board and said, okay, let's think about the V2, change this. And then again, if I needed 3 levels, I would need 60 code blocks, but I reduced my code time. I reduced the run time to 5 hours for 40,000 orders. So fairly good improvement. But I knew I could do better. The trend was clear. I had to reduce the number of code blocks. And so now the flowchart looks like this. I have only 6 code blocks, and it takes about 1 hour to run 40,000 orders through the simulation. Of course, it comes at a compromise. Everything you code in code blocks, you have to code it in, functions, objects, triggers, dynamic events, and these kind of things. But yeah, I'd recommend when you start, use a lot of code blocks. And as you improve and scale up, you need to reduce that and start coding with functions. So yeah, in the last 5 minutes, I can show you the use case that we've had, one of our use cases, our first main one actually, and how that helped improve the efficiency of a factory. So it was about Aura, this routing algorithm that I mentioned before, which decides where each box goes. And the decision is for each box, which ingredients we pick from which stations. The objective is, of course, to maximize throughput. And it looks like this. You have a box, and the algorithm will say, well, you go to station 1, pick carrots and potatoes. Station 6, pick this and that. And then station 4, and then you can exit. And that's a bit how this algorithm, the description of the algorithm. And actually, you can't really code throughput in the algorithm. And so that's where the simulation comes in, because when you make changes, you of course maximize your objective function, but does that really correlate to performance in the factory? It's really hard to tell. You need a simulation to tell you that. And so when we're far enough in the simulation, it's like, okay, let's make a new version of Aura. We want a 50th iteration. So let's make a new version of Aura. We can use a simulation to develop it and to test the different changes. And so here a few of the changes that happen between V4 and V5. V4 had big batches of orders routing at the same time and empty initialization, so we didn't consider what was live. V5 is we route smaller batches more frequently, and we initialize the stations with the workloads that's currently there. And also, in V4, we didn't consider stock, so we assumed perfect stock, whereas we know that we have always stock problems, and so we decided to include stock coverage in our V5. Now, before running the simulation and giving numbers, a main question with stakeholders is like, how do we trust the simulation? How do we know that the changes will apply to the factory? So one of the key things we do to answer that is to run simulation replays. So we take something that happened in the factory, like a weekend or something, and we're going to replay it through the simulation and try to match as close as possible the simulation. So in this example, you have in purple the reality, and that graph shows you the number of orders we completed over time. And then we ran over V4 as it was running in the factory, and we got something fairly close to that. And there's a function for defining accuracy. In this case, we got 97.5% accuracy. And the idea is, well, if we're able to replay what happened, if we make a change, most likely it will apply. So actually, we ran 4 different scenarios. Of course, the replay one, the blue that was showed before, and then 3 different scenarios with over V5, which is basically how many changes we apply to it. And of course, we want to have as many changes as possible because, in theory, that improves production as much as possible. But we know that sometimes when you're dealing with operations, they want as few changes as possible. And so we did quite a few different simulations for that. And this is typically one of the simulation results. The results were fairly consistent. And so what it's showing is, as we had predicted, we actually gain in efficiency quite a lot. And in the same order as we expected. So if you make fewer changes, you improve quite a lot. And then the more changes you make to your algorithm, the more you improve your factory. So we did that over several weeks, averaged out the results. And so we were expecting improvements between 7 and 26% improvements in throughput. And the other key metric is station utilization, which is also correlated the same. And so we had a big negotiation phase with the factory around what we can implement and not. And because our pessimistic scenario was already quite good, the decision was made to implement something fairly close to a pessimistic scenario. And so, yeah, we were expecting improvements between 7 and 17% increase in throughput. So we monitored the factory over a certain number of weeks and recorded the average station utilization before that. We clicked the button for release of over V5, and that's what we got a few weeks after. And so the trend was really clear. We got a 13% improvement in station utilization, also translated into throughputs, and basically into cost of the factory with a single software release. So that really consolidated the fact that simulation as part of operations is, really groundbreaking to improve the performance of your assets. I'm going to skip a bit the perspectives, but yeah, basically, we want to keep doing more of the same thing, expand more team, more things we simulate. And yeah, I have 3 minutes that maybe I can open up for questions. How do I see questions? Q&A, there we go. So I guess I'll start with is Gousto better than HelloFresh? Of course it is. What is the duration of simulation being done by Gousto? Yes, our typical simulation now is over a weekend batch, so between 36 and 48 hours of production, and we simulate that in about an hour's time. And for now, we're not evaluating weekly plans. We only use the simulation to evaluate the week-on-week performance, and it's really code-oriented. So let me look at another question. Yeah, what is the main simulation goal for Gousto? Why do you need a simulation tool? Would another algorithm method work too? If not, why? So we really need a simulation, and we can't use something else because we need a way to evaluate the actual impact in the factory. And we have a lot of algorithms that work in conjunction that each have their own objective functions, but sometimes you're not sure they're going to work. Sometimes they will clash and not have the actual result. So you need to put them all in the same environment to see what's the actual effect. Yeah, machine learning and things like this, I think it's good. We're trying to replicate factory performance in a machine learning environment, but you can't really change your code inside of it. And then, yeah, do you do the what if analysis with MLflow or within AnyLogic parameter variation experiment? We do that with MLflow. So our wrapper includes MLflow, and that's how we then do the rest of analysis. And the final question for the last minute: does the computation time required by the Python algorithm play a role in simulation results? So yes, it's kind of the bottlenecks right now, the simulation time. It's taking us, most of the time now it's running the Python algorithm. So that's something we need to look into.